Intermediate Algebra Section 4.4. We have graphed inequalities in one variable on the number line so far in Chapter 4. We're now going to graph inequalities in two variables on a plane. And to do that, we want to do a little refresher here of graphing a linear inequality by looking at a linear equation in slope-intercept form. When you have y by itself, you can determine the slope of this equation by setting it equal to the coefficient on the x term, again provided y is by itself. And in terms of graphing, slope describes the ratio of the rise over run, the vertical displacement over the horizontal displacement of that line. The plus b is our y-intercept, and it has the point where the coordinates 0, b. It's where the line crosses the y-axis. So let's take a look at graphing this linear inequality. When you graph a linear equation, you have a line. When we're replacing that equal sign with an inequality sign, we have what we call a linear inequality. The solutions of the linear inequality are ordered pairs. And so we will kind of ignore temporarily the inequality sign and treat this as though it was a linear equation with an equals in it. It is in slope-intercept form, so this is a way of graphing this inequality. You can pick points, or you can graph this linear inequality by its x and y intercepts. But if I continue on here, since y is by itself, the coefficient of x, which is our slope, is equal to 1. That will be our ratio for our slope of rise over run. 1 has a denominator of 1, so there we have a ratio. The signs agree here, so b is equal to 2, so our y-intercept is going to be at 0, 2. And we'll go over here and we'll graph that information. Starting always here with the point, we need to have an anchor. It's our y-intercept, the point, and then we'll move away using the slope of 1 vertical rise for every 1 horizontal run, and continuing on up 1 over 1. Now, before we just automatically draw the line, we have to look at the inequality. This is a greater than or equal to, and since it's equal to, the line is going to be included in the solution. And to show inclusion, we will draw a solid line. Once we have the line, we're looking for all of the values that have y greater than this line, and all these points above the line, the y value is getting larger. If you just look at your y-axis, the y values are getting smaller, so every ordered pair would have a smaller y, and we want all of the ordered pairs where y is greater than or equal to this line. The equal to, again, is indicated by the solid line, and we want everything that is on this half of the graph. When you're in my math lab and graphing this, you'll have a bucket, a fill, so that you can click on the bucket and fill what we call a half plane. The graph of this linear inequality is a half plane with a boundary that is this straight line. In this next example, they're asking us to graph this inequality, y is greater than 1/2 x. To graph this, I'm going to compare it to the slope-intercept form of an equation. There is nothing being added on, so the implication is b is equal to 0. Since y is by itself, the slope of this line is 1/2, which is going to give us the ratio of rise over run. As I previously mentioned, our y-intercept, our b value, is 0. So when we graph this line, we always start at our y-intercept, which is at the origin. Our slope on this line, for every 1 we rise, we will run 2. For every vertical up 1, we run horizontally 2. And in this linear inequality, because we're looking for all the points that have y values greater than this line but not including this line to show that the line is not part of the solution. We draw the line with a dash. So someone looking at this sees the dashed line. It's our boundary, but our solution is not drawn from any of the points that are on the line. What points we are interested in are all the points that have y values greater than the line. And to determine that, look at your y-axis. The values are greater above the line than below the line. And so we would color in or fill in the entire upper half plane for a solution. And just to help illustrate what we're doing, if we pick a point in this shaded region, for example, this point here has the coordinates 1, 2. This point should satisfy this inequality. So just for a check, I am choosing y to be 2. So in the linear inequality that's given, we'll put a 2 in place of y, a 1 in place of x, and see if we get a true statement. 2 is greater than 1/2 times 1 is 1/2, and we have a true inequality. We would expect it to be true given that the point is part of our solution. Had we tested a point down here, say 2, -2, the coordinate of that point, because it's not part of our solution, we would not expect a true inequality. If the linear inequality is not in the best of shape, we can transform it, again, depending on your graphing method, picking some points to graph your line, graphing it by its x and y intercepts, or here, again, I'm going to illustrate graphing this using the slope-intercept form of a linear equation. So I need to get y by itself. I'm going to divide every term by the coefficient. I end up with a -2/3 x, and because we have an inequality and we're dividing by a negative, the direction of the inequality must change. The negatives cancel out, 3's cancel out, giving us y. Comparing this, I can either turn it around or leave it as is and put my mx plus b is equal to y for our slope-intercept form to pull off the components that we need. The coefficient on our x term is our slope, and our slope turns out to be a -2/3. If you look up here, I divided both sides by -3, and when I rewrote it, I floated that negative up to the numerator. I could have left it in the denominator. Ultimately, this is just a negative expression. When you take a negative divided by a positive or a positive divided by a negative, the result is negative. And sometimes they'll put that negative right in front, even with your fraction bar. For graphing purposes, it's best to have the negative either in the numerator or in the denominator. It can't be in both because that would cancel out and give us positive. And we do have a negative slope for this graph. There is nothing being added on to our x. There's no constant term in this inequality. So like the last graph, b is equal to 0. That means our y-intercept, 0b, will be at the origin for this linear inequality. So here we have our graph. We always start with our y-intercept, the origin, and your pick. If I choose the -2/3, that means I'm going to rise a -2, which is dropping down 2 for every 3 that I run. Or I could have risen a +2, but if I go up 2, then I need to run -3. And if you notice, those points are all in a line. They're collinear. This linear inequality does not have the equals. It's just a greater. So when we connect those points, we will do so with a dashed line to show that this set of points contained in this line are the boundary of our half plane, but are not part of the solution. As it turned out, we have y greater than this line. If you read from the right to the left, we could rewrite this, but when you switch this, you have to make sure that inequality is still in the direction with the y as it should be. So we're looking for y values again that are greater than this line. That means we will be shading above the line everything here, and I'm not filling it in entirely, but hopefully you get the idea. And again, you could pick any test value on this upper half of this plane for a solution and see that it does work for this value. I'm shading above because the y values in every one of these points are larger above than here. The y values are getting smaller. In this linear equality, it's set up again. We have y is equal to mx plus b, using that slope-intercept to help us pull off the components and graph this. The coefficient of our x is a minus, shorthand for a -1, so we have a slope of -1. And because of a ratio, we can put it that implied denominator of 1 so that we have a rise over run and can move away to graph our line. The plus b doesn't agree. Here we have a -2, but if you use your rule of subtraction, which if you have a subtraction you can add a negative, I can change a -2 into plus a -2, which means b is equal to -2. Our y-intercept of 0b then will be a 0, -2. Always starting with the point at 0, -2, where the line crosses the y-axis, and moving away with a rise of -1, means I'm going down 1 for every positive horizontal, down 1 over 1, and so on. In this example, we are including the line, greater than or equal to the line, so our boundary set of points in this line are included. To show the inclusion, we'll use a solid line. And in this one, we're looking for y values greater than this line. The y values above the line are greater, smaller below. So if you are thinking above, you'd be exactly right. So every point on this upper half would be a solution that should satisfy that linear inequality. The last example I want to show you is a system of linear inequalities. To graph a system of equations, we graph the individual equations and then find the intersection of the graphs. We work similarly with a system of inequalities. We graph each inequality and then find the intersection of the graphs. And this may not look like a system, but it's a combined inequality that we are going to have to split up and take a look at each one of these equations. This is red, x is greater than or equal to -3, less than or equal to 3. So I'm going to use that to pull these apart. X is greater than or equal to -3, and x is less than or equal to 3. We're using our skills that we covered earlier with our combined inequalities. Now, this doesn't look like a y equals mx plus b. When you have an x equal a constant, it's a special linear equation, if you recall from earlier in this course. And you may know right now that that's a vertical line. Great. If you are plugging values in to come up with your equation to graph here, there's no y value here. We can put a y in. If I put 0 times y plus x greater than or equal to -3. The 0 times y is still 0 and gone. I haven't changed anything, but at least you can see as you pick your y values, whatever they are, they can be a variety of values, they get zeroed out. X will stay a constant -3. So what it results in would be some points of -3, 0, -3, 1, -3, -1. The y can change because it's zeroing out. The x is going to stay equal to a -3. We'll deal with the greater in just a minute. So vertical line, whether you plot these points, -3, 0, -3, 1, -3, -1, when we're graphing x, and we're thinking here x equals a -3, it's a vertical line. Because it's included, it will be a solid line. Every one of the points has an x equal -3, but the y's are changing. And we want x values that are greater than this line. Well, the x values are getting greater on the right-hand side and smaller on the left. So our solution here would be everything to the right of this line. But we're looking for the intersection with this set of points, or this linear inequality. The associated equation is x equals 3, and the same analysis that I just went through here, y is in this equation. 0 times y plus x is equal to 3. Regardless of the y value ever changing, x stays steady at 3, and when you plot that, you will end up with a line at x equal, a vertical line, x equal to 3, represented here. In this inequality, we want x less than or equal to 3. Let me use a pencil to show what that is. For this graph, and we are including the line so it's solid, we want values of x that are less, so values of x are less to the left, so it would be going off all the way on this half of the graph. And here's where now we consider the system of linear inequalities and looking for the intersection. What's common between the two? Well, you can see the common is where I've got those cross regions, cross lines. So the intersection of these two will be the common points, and the common points are here in the alley, including up to and including these two vertical lines.